All right, so we'll get started. Um, so this is the upcoming schedule for this class. Next homework will be due on Tuesday next week, okay? And then 6 will be due a week after next one's due. And exam 2 is scheduled March 5th, which is a Friday, okay? It's the Friday after the midterm break, okay? Um, so that's the schedule for the next few weeks. Um, Today's in-C classroom disinfection is assigned to Ryan um, and Parker. Okay. Um, so let's get started on the lecture part. So last time we took a look on electric potential due to a point charge. So if you have a point charge in space, it will produce an electric field. So then the potential at any point that is r away from this point charge is equal to this. Okay, so V, capital V for electric potential, which is K, the Coulomb's constant, times Q, the charge, divided by the distance from the charge, okay? And then for the potential energy at that particular point for any point, any charge Q, 0 there will be equal to this guy, okay? Energy will be equal to the charge times the potential. All right. We also talk about the equal potential lines where on the line that you have electric potential as constant. So the green curves here, each of the green curves or green circles here, they are equal potential lines. Okay, so that means on any of the green, any points on any of these green lines, their potential is the same. All right. And equal potential line will be perpendicular to the electric field line, as you guys saw last week in the lab, okay? All right, we also talk about capacitors and dielectrics. So capacitors have the ability to store both charge and energy, okay? So for the capacitance, which characterize the capacitor, is equal to the charge divided by the voltage built up between the two plates. So typically you have two plates for the capacitor, okay? And that C is for capacitance. It's in farad as the SI unit or F, okay? For a parallel plate capacitor, its capacitance is proportional to the area of the plate and inversely proportional to the separation of the two plates, okay, with this epsilon naught as the permittivity of free space or vacuum as a constant number here, down here, okay. All right, if you insert insulator, or we can call it dielectric, in between the plates of a capacitor, then the capacitance of the capacitor will increase by the amount of the dielectric constant kappa, okay. So kappa is material specific. So for each material, it has its own kappa. So then in that case, electric field produced between the plates is reduced by kappa, but the capacitance is increased by the factor of kappa, okay, the dielectric constant. So for a dielectric or an insulator, if you apply the voltage that is high enough, then you can actually break it. Okay, so then it will become conductor. So that's called dielectric breakdown. So for different materials, the dielectric breakout voltage are different. Okay, so for example, for mica, you need to have the dielectric strength, or this is the electric field strength, to be 100 million volts per meter to break down. Okay. You can find them here. Okay, so just keep in mind that if you have very large electric volts or electric field, then the electric will break down, it will become a conductor. Okay. All right. So let's take a look on how much energy will be stored in a capacitor. Okay, so when you charge a capacitor, you actually charge it either with a battery or a power supply. Okay, so then the voltage V will build up. Okay, so voltage will go from 0 to the final voltage, okay, of V. So in that case, you can imagine if you want to move amount of Q from one place to the other place. So that's the actually the charging process. So the charging process removes charge from one plate and deposit into the other plate. So then one plate will be negative charge, the other plate will be positive charge. Okay, so you can imagine moving the charge from one plate to another plate. The energy or the work done required should be equal to the energy, okay, difference of the charge going from one plate to the other. So you'll do Q times this time because V goes from 0 to a final V. So you'll take the average voltage, okay, which is equal to 1/2 of the final V. So then potential energy or the work required is equal to 1/2 of Q times V. That is the energy being stored in the plate. Okay, so this is how much energy is being stored. Now, you can express this also in terms of the capacitance because Q is equal to C times V, or if you look at the definition for capacitance C is equal to Q over V, all right? So then Q is equal to C times V. So this can be equals to 1/2 C, the capacitance times V square, okay? So either this one or this guy here. You can write V in terms of C from C equal to Q times C equal to Q over V. So V is equal to Q over C. So then it becomes Q squared divided by 2C. Okay, so 1/2 still is here. So any of those three expressions will give you the energy stored in the capacitor. Okay, so either 1/2 Q times V or 1/2 CV squared or Q squared over 2C. All right. Now it depends on what quantities are given. You are going to pick among those three expressions for the problem. Okay. We will take a look on the example here. So this one says if you have a parallel plate capacitor with plate 0.0440 meters square, that's the area, the A, okay, and plate separation 85 mu m micrometers. So that's D is to be charged to 12.0 V, okay, so that's your V voltage, and store 7.50 microjoules of energy. What should the dielectric constant of the material between the plates? Okay, so let's visualize the problem here. So in this case, you probably have like a double plate, parallel plate capacitor, okay? And it indicates there's a dielectric. So in between, you fill it with certain dielectric material. Okay, so something like that. In red, that's the insulator in between. It's a layer of insulator in between. Okay, it tells you the area 0.0440 meters square. It tells you this distance d between the plate. Okay, that's 85 micrometers, so it means times 10 to the 6 minus 6 meters. Okay, so the voltage across V is equal to 12.0 volts, and it says the energy stored is equal to 7.50 times 10 to the minus 6, okay, microjoules. It's asking you what's this dielectric constant. Oh, actually kappa, sorry, not the permittivity. It's asking for kappa. Okay. So these are the equations you might want to consider. For energy store, it's equal to either 1/2 of Q times V or 1/2 of CV square, or Q squared over 2V, okay? And for capacitance C, if you have dielectric in between, it's going to be kappa epsilon naught times A divided by D, all right? Epsilon naught is the 8.85 times 10 to the minus 12 farad per meter, okay? You're looking for kappa, all right? I think I can give you guys a couple of minutes to see if you can solve for this one, and we can take a look at the solution together. All right. So let's take a look here. So you're looking for kappa. Okay. So kappa is associated with the capacitance, right? So you can see it gives you D, gives you A. So epsilon naught is the constant. So then if you know C, you can figure out kappa, right? So now the question becomes, how can you figure out C here? So C can be related to the energy store. Energy is equal to, so in this expression, the second one has the capacitance C in it. Okay, so you're taking the second expression there. U is given, V is given, so you can figure out C first. Okay, so you can calculate C and then take C into this here, and then solve for kappa. Okay, so that's how you can do it. So we are going to use CU equals to 1/2 CV square, and then so from there you will get C is going to be equal to 2 times U over V square. Okay. Then you can set it up that this is equal to this expression kappa of epsilon naught times A divided by D, right? Because that's also equal to C. Then from here you can isolate kappa to solve for kappa. So kappa will be equal to 2 times U times D over epsilon naught times A over V squared. Okay, so this is algebra there. Then you can just type in the numbers 2 times. So just keep in mind this is 7.5 times 10 to the minus 6 microjoules. Okay, D is 85 times 10 to the minus 6 meters. All right, divide by 8.85 times 10 to the negative 12. And then the area given as 0.440 meter or 0.0440 meters squared over the voltage 12V squared. Okay. Then you can solve your kappa to be 22.74. All right. The dielectric constant doesn't have a unit. Okay, it's a ratio between the permittivity of material to the permittivity of vacuum, so it doesn't have a unit there. As long as you have everything in SI unit, then it should be just without dimension there. All right. Any questions you guys might have on this one? Okay. All right then. So if that's clear, we can move on. So a lot of times you are having several capacitors and then you want to combine them. Okay, so it's not as simple as like you have a one capacitor that fits all the purpose. Okay, so a lot of times you have different capacitors. So let's see if you put them in series or yeah, so typically you will put them either in series or in parallel, or maybe combination if you have more than two. So you might be having some of them in series and then after that with in parallel with the others. Okay, so a combination of in series and parallel together. But let's just take a look if they are purely in series and in parallel first. Okay, so the first we are going to look at if you have two capacitors, they are in parallel to each other. So this guy is in parallel to that guy, okay? So in parallel means their potential differences are the same, okay? So that means this capacitor after it's charged will be having the same voltage as this capacitor number 2, okay? So C1 and C2. In a circuit like this, usually C denotes the capacitor. Okay, so if you see C1, that means one capacitor 1, C2, that means capacitor 2. All right, now typically you would have them charged, so either with a power supply or a battery, so you get like voltage across the terminals A and B. Okay, so voltage A, voltage B, then that gives you a difference. Okay, you'll do VA minus VB to get the voltage across the two plates. Okay, so after they are charged in this combination, then they are in parallel. Okay, now in some abbreviation for capacitors, you are if this is in a circuit, you'll typically see two parallel lines, the same length. Okay, next to each other. That's the symbol in a circuit for capacitor. Okay, if you see two lines, one is short, the other one is long, that means it's actually a battery. Okay, so pay attention to the symbols here, or the representations of the different elements there. All right, so if you have two capacitors are in series, that means their voltage across the plates are the same. All right, so you can calculate how much charge is being deposited into the plates. So for capacitor 1, you can calculate as Q1 equal to C1 times V. All right, for the second capacitor, the charge deposit on the two plates will be equal to Q2 equals to C2 times V. All right, so V and V will be the same. So you can, so then for the total charges stored on the two capacitors combined, you can add them up. Okay, so then total Q is equal to Q1 plus Q2 equals to C1V plus C2V. The V's are the same, so you can single out the V. So C1 plus C2 times V. Okay, so then you can see, so for combination of these two capacitors, if you treat them as a just a combination of capacitors, so then you can replace with it with a equivalent capacitor. Okay, so you can use so then the equivalent capacitance of that one, so in this case, so let me see, yeah, so just focus on these two. Let me see if I can, think I used this one to just block that one. All right, so then we'll be just looking at two capacitors, okay, in parallel to each other. Okay, so in this figure, you'll see like the two lines close to each other that represent a capacitor. Over here, you have one longer line, a shorter line, so that represent the battery, okay? So battery, the voltage supplied by the battery usually is represented by epsilon, okay? So that's that stands for the voltage for the battery. Now for the longer line, it's the positive terminal. For the short line, that's the negative terminal, okay? All right, so as I said, if you have two in parallel, you can replace it with an equivalent capacitor. Okay, so then this one acts as the combination of those two. All right, so then for the equivalent capacitance for the combination, it should be just equal to C1 plus C2, right? So if they are in parallel, then you add this capacitance up, okay? Because the total charge is equal to Q1 plus Q2 or C1 plus C2 times V as shown in the last slide, okay? So then the equivalent capacitance is the combination of the sum of the two capacitance for the two capacitors, okay? If you have three, then equivalent should be equal to C1 plus C2, C plus C3 if they are in parallel to each other, okay? All right, like this. So if you have three, you simply add them up if they are parallel to each other. Okay, if you have more than three, then you add the rest up, okay, as well. All right, so this is for equivalent capacitance for capacitors in parallel. All right, simply you just add them up. A quick example here. So it says if you have 36 microfarad capacitor is connected in parallel with an 18 microfarad, should be F here, okay, for the typo there. What's the equivalent capacitance of the pair? Okay, so these two are in parallel, so you'll add the capacitance up. Okay, so 36 plus 18, all right, will give you 54 then in this case. Okay, so this one will be simply, you just add the two up. Okay, so this, they are in parallel, so C equivalent should be equal to C1 plus C2, 36 plus 18 will give you 54. Okay, so they're in parallel. All right. Just one out there. Okay. Let me know if you might have questions on this one. Okay. All right. So if not, next we will check capacitors in series. So okay. So when they are in series, that means you connect them one after another. Okay. So those three, for example, if you have three capacitors, so then they are in series in this pattern. Okay. And they are charged by the battery over here. So you can replace those three with an equivalent capacitor. Okay, so then this one stands for the combination of those three. Okay. When they are in series, that means they are connected one after another. So that means the charge across the plates are the same. Okay, so because when you charge a capacitor, you basically move the Q from the positive, typically you remove the electrons, okay, from the positive place to the negative plate, okay. So then that Q and this Q will be the same. So this will be negative of that, this will be positive of that. And then this will be negative of that. This will be positive of that, okay. So the Q across will be all the same because net charge initially, because you are just moving electrons from one plate to another plate, okay. So according to net charge should be equal to 0. So then, so this is just simply redistribution of the electrons, okay. So all the charges. So so Q's will be the same, all right. So then Q on this one, all right, should be equal to C1 times V1, okay, that equals to Q. And then on this one, Q will be equal to C2 times V2, all right. Q here should be equal to C3 minus V3. So you can see the V's on each of the capacitors will be different, okay. Let me see. All right, I think deviation is missing here, but I can show you guys quickly on this one here how to derive the formula for the capacitance are in series. Okay, so when they are in series, so then on Q1, Q is equal to C1 times V1. On the second one, the same Q is equal to C2 times V2, and then on the third capacitor is equal to C3 times V3. All right. The V across each capacitors, you will add this one V1 plus V2 plus V3. Okay. So if you add V1 plus V2 plus V3, that should be equal to the potential across the battery as the power supply. Okay. So that should be equal to this epsilon there. All right. So you can rewrite this. So this guy, V1 is equal to Q over C1 plus Q over C2 will be V2 plus Q over C3 will be the V3. Okay, and that equals to epsilon. Okay, now if you replace the three capacitors with this guy, simply this guy, right? So then epsilon will be equal to this Q equivalent CEQ times times Q. Oh, actually, no, the other way around, sorry. So the Q should be equal to the capacitance times the voltage, which is epsilon. So C of equivalent, okay? So now in this case, from here, you can see epsilon is equal to Q over C of EQ, okay? So then take this in the expression, you'll get Q over C1 plus Q over C2 plus Q over C3 equals to Q over CEQ. All right. So in that case, all right. So in that case, the Q are the same across, so you can cancel them out. So then 1 equals to one over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over CEQ. Okay. So then in order to calculate the equivalent capacitance for the capacitors in series, you will do inverse of each of the capacitance and then add them up. Okay. To get the inverse of the equivalent. All right. So then for C of equivalent, and then should be equal to 1 plus 1 over C1 plus 1 over C2 plus 1 over C3. And then take an inverse, okay? So that's what you want to pay attention to. You're not simply just doing the inverse and then adding and then up, but after you are doing the inverse of each one and then add them up, you want to do inverse of the sum, okay? So this is equation for CEQ. Okay, so remember, it gives the inverse of the capacitance. Okay, not the capacitance itself. If you have more than 3, you just do inverse of each one and then add them up. Okay, so add the rest inverse of the rest up and then doing inverse again to get the CEQ. Okay, all right. So this is for capacitors in series. And on capacitors in series, we will take a look on one example here, and then I'll have you guys to solve for the equivalent capacitance here. Okay. Again, just remember you want to do the inverse of each capacitance, add them up, and then after that, doing inverse again to get the equivalent capacitance. Okay. All right. So I think we can take a look at this one together now. So there are 2 of them in series. Okay, so you want to then use the equation of 1 over CEQ is equal to 1 over C1 plus 1 over C2 because there are only 2 of them. You're looking for CEQ here. All right. So then actually CEQ is going to be equal to 1 over C1 plus 1 over C2 and then inverse of it. Okay. So remember that. So it will be 1 over 126 microfarad plus 1 over 252 microfarad. and then take inverse of it. So if you do that, it will give you your final answer as 84. The unit will be microfarad here. Okay, it doesn't ask you specifically what unit you should be using, so you can keep it microfarad. Okay. All right. Any questions you guys might have? All right. So a little bit summary over here. So if you have them in parallel, then the equivalent capacitance is simply the summation of the capacitance of each capacitors. Okay. If you have capacitors in series, then you do inverse of the capacitance of each capacitor and then map, and then do inverse of the sum. Okay, afterward. Now, in more generally, you'll have capacitors like in combination of series and in parallels at the same time. Okay, so let's take a look this example here. So you can see there are 3 capacitors here. Okay, so 2 of them are in series. All right, so then you can treat them as one equivalent capacitor. Okay, after that, so the equivalent would be in parallel with this guy. Okay, so basically, let me show you here. This is how you want to do it. Okay, so when you have capacitors that in series and in parallel at the same time, so what you want to do is start with the part that you just have capacitors purely in parallel or purely in series, and replace that one with an equivalent capacitor. Okay, so then on this one, you will have to do it this way. There's so terminal A and B, there's one here on top, and then there are 2 at the bottom over here. Okay, so now pay attention here. You want to see, so this one, these 2, they are in series. Okay, purely in series. All right, and then you can now simplify this as replace this with an equivalent. Okay, so with an equivalent capacitor CEQ. So then this becomes something like this with the original one on top, but this time you'll have just one button here as the equivalent capacitor. Okay, so then after that, um, simplify this one with this one capacitor. So then these 2 now just are in purely in parallel to each other. Okay. All right. So then let's take a look here. So your total, your final, or let me just say prime here. This is the intermediate step. Okay. So your CEQ total should be equal to, so if this is C3, this is C1 and C2 originally. So then your CEQ, now this is C3, should be equal to C3 plus CEQ of prime, which means the equivalent capacitor for C1 and C2. Okay. For C1 and C2, because they are in series, so this is C3 plus. They are in series, that means you are doing inverse of C1 plus inverse of C2, and then do an inverse of that. Okay, so this is because they are in series. All right, so then you'll get, for the final result, you'll get, I think the numbers are given in the original figure there. So 15 as C3, 8.2 as C1, 22 as C2. Okay, so then we can take those numbers in here. This would be 15 microfarad plus 1 over 8.2 microfarad plus 1 over 22 microfarad. Okay, and then take inverse of that. Okay, so it will give you 21 microfarad. Okay, for the final answer there. I think I can give you guys another example here. Okay, so let's say if you have between terminal A and B, let's see one. All right, so let's do this. If this is 8.2 microfarad, this is 22 microfarad, and then this guy will be the 15 microfarad. So in this case, what will be the equivalent, total equivalent? All right, you guys can use this as an additional exercise. Okay, so in this configuration, these two are in parallel to each other. Okay, purely. So then you replace this one with the equivalence CEQ prime first. All right, and then this guy after that. So then it becomes, the circuit becomes a CEQ prime with this 15 microfarad. Okay, so then it becomes that one. So you can calculate this first, and then these two are in parallel to each other. Okay, so when they are in parallel, you can do inverse of this one, and then plus inverse of that one, and then take the inverse. Okay, to calculate what's the CEQ. Okay, but you guys can do it after class as an additional exercise. Okay. All right. Any questions you guys might have? So if not, we are going to take a look on another subject on capacitors. So a lot of times when you are charging a capacitor, okay, and after that's done, you probably want to remove the power supply. Okay, so if you have the combination of capacitors, after you remove the power supply, then actually, because you have charges built up across the plates of each capacitor, right? Now that's imbalanced because there's a power supply, external power source. If you remove the power source, then the charges may be redistributed because charges are not all the same across each plate. Okay, so we'll take a look on this example here. It says if you have a 100 PF stands for picofarad times 10 to the negative 12, okay, capacitor and a 400 picofarad capacitor are both charged to 2.0 kilovolts. Okay, so they are charged to the same power supply, so that means they are originally in parallel to each other. Okay, so let me draw the configuration over here for you guys to visualize the problem. So there's a 100 picofarad capacitor, and there's a 400 picofarad capacitor. If they are charged to the same power source, both charged to, so you can imagine that across these two terminals, you can apply potentials of 2.0 kilovolts across, okay, across this guy and that guy. I'm going to just put positive there, negative here, okay. So they are connected to the power supply of 2 kilovolts. All right. So then next, what happens is you disconnect them from the voltage source, okay? So if you cut the voltage source and then reconnect them, okay? So what happens here? So it says in this fashion that positive plates to negative plate and negative plate to positive plate, okay? So what's going on here is now it becomes, if you cut it off and then reconnect them. So on this one here, the 100 picofarad, let me put positive here, negative here. Okay, positive plate, negative plate after it's charged. And then on this side, now you will have to flip this one. Okay, so then the negative is on top, positive is on the bottom. You reconnect them in that fashion. Okay. So this is the 400 picofarad. So you can imagine you have Q1, positive Q1 here, you have negative Q2 here, right? So the charge will then somehow it will cancel out because one is negative, one is positive, and then they are connected together, right? On this button here, positive 2 and then negative Q1 will also partially cancel out, okay? Q1 and Q2, they are not necessarily the same, okay? Because Q1 will be equal to C1 times V when it's charged. Q2, the charge on the second plate capacitor will be equal to C2 times V. The V's are the same, C1 and C2 are different. So Q1 and Q2 are different, okay? It's asking you now, find the resulting potential differences across each plate. Okay, so then what would be, it's asking what would be the V, V1, afterwards V2. Okay, you guys can think about how you can solve for this one, and then we'll take a look at this together. All right. So let's first take a look on here. Okay, so because this is connected to this one, and then this is connected to that one, right? So the potential difference across this guy, then if you use a multimeter to measure the potential difference on here, on the two plates here, right? It should be the same as the potential difference across this, right? So that means charge will redistribute it. Negative and positive will exchange, okay? Then you will get, let's see, probably, so because C2 is greater than C1, so that means Q2 is greater than Q1, right? In this case, C1 is less than C2, so Q1 is less than Q2. So minus Q2 here will neutralize the positive. So the overall, because Q1 is less than Q2, overall on the top here, you'll have negative charge, okay? So you have a negative Q2 prime here, you will have a negative Q1 prime on this, okay? So this is afterward. The same will happen for the lower plates. So charges will be exchanged. So then because Q2 is greater than Q1, you will have positive Q1 prime on here. You have actually, yes, positive Q2 prime at the bottom here, okay? So on the top plates, both will be negative. At the bottom plate, both will be positive, okay? So that's what happens afterward. So because they are connected on the top here and then at the bottom here, so if you take a voltage meter here, measure this guy and that guy, that will be the same. That means they are in parallel to each other, right? If they are having the same voltage, that means they will be in parallel to each other, okay? So then they are in parallel. C1 and the C2 are in parallel to each other, okay? All right. So I think if you figure that out, then we can treat them as a equivalent capacitor, just as a single capacitor, something like this, right? CEQ, right? Because V1 will be equal to V2 because they are in parallel, so that will be equal to the V that you are looking for, okay? So then you're looking for the V across this guy, okay? CEQ, because they are in parallel, so then you can calculate what's this CEQ, right? So CEQ, because they are in parallel, should be equal to C1 plus C2. You just add them up. So 100 micro pico plus 400 picofarad. That gives you 500 picofarad, okay? For the CEQ. Now, in order to figure out V voltage C, according to C equals to Q over V, all right? And then in this case, we are talking about CEQ because that's the combination of the two. So that means you need to figure out what's Q, okay? Or the Q total after the charge redistribution, okay? So the Q total here, you can see on the top here, the total will be positive Q1 minus Q2, okay? At the bottom will be Q2 minus Q1, all right? So then that will be, the Q total will be equal to actually Q2 minus Q1. All right. Q1 and Q2 can be calculated. Q1 is C1 times V, original V. So let me put this as V0, V0, okay? Not to mix with the final V, V sub 0. All right, so we can calculate those two first. Q1 equals to C1 times V1. C1 is 100 pico farad, okay? Times 2 kilovolts. That gives you 200 times 10 to the minus, this is positive 3, minus 9 coulomb, okay? And Q2 is 400 times 10 to the minus 12 times 2.00 times 10 to the third. That gives you 800 times 10 to the minus 9. Okay. So then Q afterward, Q total is Q2 minus Q1, 800 times 10 to the negative 9 minus 200 times 10 to the minus 9. Okay. Which would be 600 times 10 to the minus 9 coulombs. All right. And then after that, according to this guy, V should be equal to Q divided by C equivalent. Okay. So Q is 600 times 10 to the minus 9 coulomb over 500 times 10 to the, so this is CEQ here, 500 pico times 10 to the minus 12 farad, which gives you 1.2 times 10 to the third voltage, okay, volts. So that should be your final voltage after the charge being redistributed, okay? So V1 and V2 will be equal to that. So V1 equals to V2 equals to this guy, okay? Both the potential across the two plates are equal to each other. All right. Questions you guys might have on this one? All right. So if not, I think that's the last slide. Let me just double check. All right. If not, then we'll stop here. Okay. We'll come back on Friday.